Hello. So let me first thank the organizers for this amazing seminar and giving me an opportunity to present my work. So basically, I work on the interface of condensed matter physics and quantum statistical mechanics. So I'll be presenting escaping chaos because even the system I work with, they don't like chaos in their life. The more technical title will be quantum many-body scars. So the beautiful phenomenon which had been studied in the recent year quite extensively. So but disclaimer is that I have used only simple pictures. So it's a crude simplification of quantum mechanics so that it can be accessible to all of them. So expert, please bear with it. So let's consider a ball bouncing within a boundary without loss of any momentum. So this is a particular boundary and the ball is just bouncing up. It will just reflect from the boundary and it just continues to moves on. So eventually what will be the trajectory of the ball looks like. So this is for like two generic boundary I have taken. So it will just look like this. It will just explore the whole space available to it. So if we start from any particular initial condition, I mean any particular position and any particular direction, and I ask you, where is the ball after a long time? So it is very hard to answer because you have to literally track each angle by angle reflection, and then let's say you do it using some supercomputer. But there is an independent effect which comes to play and makes your hard even more difficult, because if you just by chance slightly miss the initial condition wrong, then this little error will grow like a snowball, and this effect is called the so-called butterfly effect, and which is the hallmark of the chaos. So this chaotic motion of the ball, that is the unpredictable motion. So I look at on the perspective of that, it gives rise to loss of information, because whatever the initial condition is, wherever the ball starts from, the system will eventually explore the full space. It will just disperse over the whole space. Okay. So do system exist where we can predict the motion of the ball at all time? Is there any pattern? Yes. Those systems are called integrable system. For example, if just change the boundary to a circle, and if you have a circle, if you start the ball from any initial condition, then there will be a stable periodic pattern. The ball will fails to explore the full space available to it. But these systems are very ideal and very hard to realize in nature. So the question I want to ask is, can we make a smart choice of initial condition so that we can escape the chaos in an otherwise chaotic system? That means, let's say the first example, the first stadium I saw, can we make a smart choice so that we still have a predictable pattern? Yes. So for this, the example is that look at this, this initial direction. I mean, if you just push the ball any of this pattern, I mean a periodic orbit, it will just try to keep in this orbit. So this is called the name scar, because it just looks like a mark in the boundary. So these are like some other stable periodic orbits, unstable periodic orbits. Why unstable? Because if you just slightly deviate, then it will just again follow the same pattern, chaotic pattern, and it will just disperse. So okay, this is some other boundary for other So just one technical side, is there any quantum mechanical version of this? Yes. So what we do, we just replace the ball by free particle and the boundary by infinite potential and the boundary, and you just solve it using Schrodinger equation. And what we look at it, typically all the eigenstates. So in quantum mechanics, so we just look at, we can't say where the ball exactly, we just look at the what is the distribution of probability of the ball. When what is the probability that ball at any place. So this shows that, I mean the dark region shows that there is a high probability of ball finding there. So typically most of the state will look like this. I mean it will again disperse. I mean the ball can be anywhere. But there are very few states which will just like follow the classical pattern. That means it will have high overlap of finding the ball at this unstable periodic orbit. So this is called the quantum scar. But life is not so simple. We have multiple particles and we have interaction. Let's say I will just simply tell you one example, just briefly, without going into details. Okay, let's say we have L balls, L interacting ball, and what is the interaction? That the ball can be changed color interacting with its nearest ball. That means the ball can be color or colorless. So the interaction, let's say there is some interaction which changes the color. So simply look at this graph picture. So what it says is that, so all the nodes are all the possible configurations of the ball. I mean, how many ways you can arrange this colored or colorless, and that is some concern, I don't want to talk about it. And what is the link is that the interaction between the ball. For example, let's say you start from this. So these balls, this arrangement of ball interact with themselves and change the colors to go to this configuration and this configuration. Similarly, from this you can go to this configuration and this configuration. Technically, the adjacent matrix of this graph is called the Hamiltonian, and the system will evolve under it Hamiltonian. But okay, just look at the simple picture. Let's say this is a man where it has his home here, and these are like other cities, and these are the roads. So I just want to ask, if the man starts from his home at time t equal to 0, where will be the man after time t? Again, we are dealing with quantum mechanics, so the man has some probability distribution. It can be at a particular city, but with some probability. We cannot say that, okay, it is at particular this city at this time. So we just do it using quantum mechanics. But what the result is that after some time, we will see that the man is omnipresent. That means man has probability of finding the probability of the man is equally distributed over all the cities. So that means the same phenomenon that happened earlier in the classical picture exists in the many-body picture. That means that it just distributed, the probability just got distributed. Okay, now we just ask the same question again. Can we start from a point such that it has the finite chance of coming back? That means just like the stable periodic orbits that is there. I just want to ask that if man has some chance of coming back to his original home, because we don't want him to stay away from home. So does car exist in this many-body picture? So for example, if you just start the man from this configuration, I mean this city, then what we will see after some time, okay, the man has probability distribution like this. That means it distributed over all the nodes, all the points. Then again, after some time we will see there is a finite chance, there is a finite chance that man come back to his original position. Then again it will be distributed. Then again it will be come back to its original position. So this, this light says that, it has very less probability of staying here. Okay. So mathematically, if you just look at the quantity called return probability, that means what is the probability that the man comes to its original position, and if you just plot it, so what you will see, so this is for the corner state here. If you just start from this state and look at the time, so it has at certain period, certain amount of time, it has finite probability that it will come to its original position. And if you start from any arbitrary initial state, you just look at it, just the probability is 0. It means why 0? Because let's say I have taken this for L equal to 24. The number of nodes is 1 lakh. So if it's equally distributed, so it will be like 1 by 1 lakh. So it is like very low. So this is the picture of scarring, but with many bodies. So okay, I am not talking just something, so it has been experimentally verified, where there are like 51 interacting ball, let's say, and the number of nodes is like, you can see the numbers, 10 to the power 7 or 8. So there also they have seen some oscillations in certain time scale. So it is experimentally verified. So after that, there has been extensively studied. So what my contribution is like, what the questions I am trying to answer, like there are two questions I am trying to answer. The first one is, given the nodes and links, technically given the Hamiltonian, what are the good starting points so to escape the chaos? Let's say we have this picture, where can I start so that I can come back to its original position? That means I can predict something. So technically, given Hamiltonian, if scarce state exists, what are the scarce state? Or the second question is that, given nodes, given cities, and given a starting point, what are the links? What are the interaction? What are the roads I can build so that I can come back to the original position from where I start from with some probability? So these are the two questions I am trying to answer. So far we have this one work done, that means predicting this thing in the spin one dimensional spin 1 Kitai model, and we are now working on this thing in transverse field Ising model. So yeah, I like to conclude. Okay, this is not visible. Some famous quote I copied from my recent talk, from ICTP that to learn more and more about less and less until I know everything about nothing. So thank you. Maybe I have some time.
Thanks a lot for this very nice talk. Do you have questions?
Hi. Like this UPOs that you talked about, unstable periodic orbits,
Yes.
they are basically the basis for chaos control, whereby giving small nudges to the parameters, you try to make the trajectory in a classical system
Yes.
go to the stable manifold and thereby stabilize this thing.
Yes, sir.
Is there an equivalent analog for quantum systems that you can think of?
Single particle. I mean, this
Yes.
one. This is the picture I.
Well, right. So
Yeah.
can you generalize this for a quantum system? I mean.
So this is the quantum picture. So
Right. No, I'm saying that, but this is not a stable system, right? I mean, or rather, suppose I start from some arbitrary initial state.
Yes,
Can I take it to the analog of the UPO?
okay,
quantum
from
system?
starting from any initial
Yeah.
state, can I go to this?
Yeah.
No. This is very. I mean, these are very fine-tuned. I will say
All
this
right.
pattern.
But there is nothing analogous to this control of chaos that you do in classical systems.
No, I mean, quantum mechanicality is very hard to.
Just just a quick question. Was it clear from your talk? So these results you're getting, are they like proven, like exact results, theorems that are proved, or are these based on sort of simulation?
This the pattern we are showing.
Yeah, no, you showed that graph and all, right? So those are based on simulation, but you said you have some.
These are like actual Hamiltonian actual system. We are just mapped to. This is a theoretical mapping of actual system. So this is our system exactly.
And these are solved exactly, is it?
So these are solved theoretically exactly.
Okay,
Yes, exactly.
thanks.
And this is the mapping to. Yeah, this particular experiment is mapped to that.
Okay, thanks a lot.